Okay, question 3 brings us into covalent bonding, simple molecular substances, and all the issues that go along with that, like shapes of molecules, polarity, intermolecular forces. This has now moved quite a long way from stuff that you may have been familiar with from school, so you need to make really sure that you get your head all around it. Don't just try and bluff your way through these questions. Okay, so first thing asks us to define electronegativity. So that's the ability of an atom of an element to attract the electrons in a covalent bond. You've got to specify in a covalent bond. Okay, because there are lots of different things that depend on attracting electrons. Ionization energy does, for example, but electronegativity applies specifically in the case where it's how strongly does it attract the bonding electrons. Okay, and then we can apply electronegativity to look at the polarities of these two bonds. So the first one is NF, and if we look at the table, we can see that fluorine has a bigger electronegativity, and that means it pulls the electrons more strongly towards it, so it becomes delta negative. Okay, remember, electrons are negatively charged, so if the fluorine's pulling on them more strongly, it becomes a bit negative, and that's what the delta means. Just, we're not specifying how negative, just means a bit. And of course that means that the nitrogen will be delta positive because it's losing out on the electrons. On the other hand, when we come to NBr, you can see now the nitrogen is more electronegative than the bromine, and so this time the nitrogen will be delta negative and the bromine will be delta positive. Okay, so that was relatively straightforward. The next bit is getting into shapes. And first it asks you to just state the shape of SF6. So this is one of the classic examples that you have hopefully learned. The answer is octahedral. And the key is that, you know, it's very unusual to have 6 atoms arranged around a central one like that. So as soon as you see that, you should be thinking octahedral. Okay, the next part is a real old chestnut, BF3 compared to NH3. Again, these are examples that you've almost certainly learned when we first did shapes and things, but this time you've got to go through the whole business of doing the dot and cross diagrams and using those to explain it. So dot and cross are fairly straightforward. Let's do BF3 first. So there's the boron in the middle, and we want 3 fluorines around it. Okay, 1, 2, 3. And the key thing to remember is that boron is in group 3. You don't have to remember it, you can see it in your periodic table, and that means it has only 3 electrons to play with, so it's going to make 3 shared pairs. And that's it as far as the bromine is concerned. It can't make any lone pairs because it hasn't got any electrons left. Fluorine, on the other hand, is in group 7, so it's got 7 outer shell electrons, and it's only used 1 in making that shared pair. So each of the fluorines will have 3 lone pairs, like that. Okay, and it's important that you show those. You know, they don't matter when it comes to the shape. It's only the lone pairs around the middle atom that are important there, but they've still got to be there when you draw the dot and cross picture. Ammonia, on the other hand, has again an atom in the middle, which this time is nitrogen, and 3 hydrogens around the outside. And again, there'll just be a single shared pair for each bond, because hydrogen has only 1 electron, so that's all it can do. But the crucial difference is that nitrogen's a group 5 element, so it has 5 in its outer shell, and it's used only 3 of them to do that, so it will have a pair of electrons left over, and that is a lone pair like that. So those are your dot and cross diagrams, and then you have to use those to answer this question about why the bond angles are different. So again, there is a general strategy for doing shape explanations, and it begins with the idea of explaining that the shape depends on repulsion between the electron pairs in the outer shell of the middle atom. Okay, and if you just state that to introduce your answer, that's quite a good way to do shape questions. So the shape depends on repulsion between electron pairs, and it must be pairs, repulsion between electron pairs in the outer shell of the middle atom. And then, having stated that, you can just simply state what there is in the outer shell of the middle atom in each case, and it's the difference in that list which accounts for the difference in bond angle. So what you can say is that boron has, in its outer shell, as we've already said, 3 bonded pairs and no lone pairs. Whereas when we come to ammonia, the nitrogen has 3 bonded pairs plus 1 lone pair. And it's that difference in the number of electron pairs repelling one another that accounts for the difference in shape. Now that would actually be enough to get you the marks here, but what would be good in other questions, at least you would have to do this, is to go further and say, well, what shape do you actually get? So when you have 3 bonded pairs and no lone pairs, the shape is trigonal planar. So you didn't have to mention that here, but it's worth reminding yourself of that. That means the shape is trigonal planar, which has a 120 degree bond angle. On the other hand, when you have 4 things repelling each other, it won't be planar. It'll be based on them pointing more or less to the corners of a tetrahedron. And when you have 3 bonds and 1 lone pair, the shape you get is called pyramidal. And that has the 107 degree bond angle. Okay, so much for that. The final thing it asks you to do is to suggest why, even though BF3 has polar bonds, the molecule itself is not polar. And that again is about the shape of the molecule, and in particular about the symmetry of that shape. So you don't have to draw it, but I think it's worth doing that to make sure you understand what's going on here. That the molecule is absolutely flat, like that, with 3 regularly spaced fluorines around it like that. And that high degree of symmetry means that although these individual bonds are polar, because the fluorines are all delta negative, the boron is delta positive, those 3 dipoles, this one, and this one, cancel each other out and add up to 0. So what you say is that the molecule as a whole has no dipole because its symmetry causes the dipoles to cancel out. And that's very useful language to memorize, because it's quite a difficult thing to explain fully, but if you just use those phrases, that will get you the marks. So the symmetry of the molecule causes the dipoles to cancel. And remember, you can get that with trigonal planar molecules like that, also with linear molecules like CO2 where the same thing happens, with tetrahedral molecules like CF4 where again the same thing happens, and indeed with octahedral molecules like SF6 where again same thing happens. So all of those are highly symmetrical, the dipoles cancel. The ones where it doesn't happen are the pyramidal ones and the non-linear ones, which have a lower degree of symmetry. And that's the end of the question.